Today my talk will be on solving energy and cybersecurity constraints in smart electronic systems. Mostly I will talk about IoT, sensors, energy harvesting sources, and if we have time we will go over something related to automotive security. So at University of Kentucky, my research group is focused on some of these areas. The primary one is the hardware security for IoT in vehicles, where we use novel computing technologies to solve these problems. And then the next one is energy harvesting and sensor for hardware security. I also work on quantum computing because that was my main research focus during my PhD time. So I still work on that. We have proposed some of the first work in these areas. But I call myself more like an emerging technology guy because I really like to work on emerging technologies. And so recently we have focused on logic in memory circuits and specifically looking how these things can be used for developing low power hardware along with resilience against side channel attacks. This is so finally today Professor Sharma has talked about smart healthcare applications. So my research group is also focusing on developing some systems for that. We have some work related to smart home environment for assisted living individuals. Then we are using also sensors for developing improving the quality of life. The major focus is on the stress detection. Today I won't talk about it, but if you have any questions, feel free to ask me actually. We have done really the actual trials on the human populations and have some real data to talk about. So today I will talk about IoT as a paradigm. So if you think in this way, this is one of the slides, I took it from Dr. Krishnamurthy from Intel. So you think in this way, this is IoT, it has applications in medical side, industrial side, retail, shopping, right, and communications. And see, this slide shows that how over a period of years, the number of connected devices are increasing. This is very interesting slide because you can think in this way, the IoT has application in your wearable devices, it has application in the smart home environment, location intelligence, and machine to machine, say example cellular GNS, right. So I will tell you one example why I switched my research to IoT domain on all those things with a real world example actually. So my mother is around 80 years old, and so I took her to US, and then actually I thought, as an engineer, how we can help the elderly people. So I thought IoT is one domain that has direct applications. So one of my first project that I started looking into is the fall detection, because most of the elderly people have the fall problems actually, they fall down actually. So I started focusing on the IoT system. Then I thought, okay, you know what, maybe as a VLSI type of engineers, we should look into developing some low power IoT systems. So I changed my focus of my research and started developing the low power, and you can say the hardware security is always a big issue. Then we thought, okay, why don't we develop systems which are low power as well as secure. That will be the primary talk about actually, okay. So this one you can think in this way, the features of these IoT devices are battery operated, small in size, they transmit data through wirelessly. So the issue is that when you have so much constraints, right, you are developing a system which is so much constraints. So you cannot use your normal cryptographic algorithms, because if you use your normal cryptographic algorithms, they will consume a lot of power, a lot of energy, right. So we need to use some lightweight cryptographic algorithms. This is the lightweight cryptographic algorithms. Now when you use these cryptographic algorithms, most of these IoT devices are battery operated, right. For example, let's think in this way, I have some sensor on the top of this building. If its battery get discharged after every 2 days, it's such a pain to go and change the system every time, right. So you need to have system which will be low power, and I place it somewhere and it remains for at least, you can say at least 2 years, 3 years, and still sending the data to me. So this one example shows that this is the desired lifetime, and you can think in this way, if your desired lifetime has to be increased, your power budget, this means should be low, right. if your power consumption is high, then your system will last only for a minute. But if your power consumption is low, then your system can last for a decade. And that's what you need, right? And this is some examples of the different types of batteries and accordingly their lifetime chart. So what are the challenges? So challenges are that you need to have energy efficiency because you want the system to run for a long time. But now if you think in this way, I want the system to be energy efficient, but I have chiseled the security. So it is much easy for an attacker to attack the system. So I need to provide some additional feature of security, right? So this a constraint is the energy efficient, the security. This one information I took it from Professor Mohanty's website. It is very nice one, where he talks about the security and the intelligence together, right? So the issue is that you have less data, you have the less computational resources, typically battery operated, energy efficient design, but you can now, this is the area that we can merge it together. They are also vulnerable to the hardware and the malware attacks, right? They are also vulnerable to the side channel based attacks. There is also issue of these IC, piracy, Trojan and all those things, right? So now we are talking about merging these two domains. You want to develop systems which are low power, but which are also secure. So this is very nice. You can look into more details on Professor Mohanty's website. He has really put some of these nice slides on those things. So the thing that I will be talking about today is the side channel attack. So if you think in this way, suppose you have a device, so you can statistically measure the power consumption of your systems, and from that you can guess what is the key that you are using for encryption or decryption, and that is called the side channel based attack. So there can be different side channel types of attacks. The attack that we will be talking about today is the power analysis based attack. So this is called DPA, that is differential power analysis, or CPA, that is the correlation power analysis, right? So the solution that we developed in my research lab, we look into energy recovery logic and for developing these low power systems. Then as I told you, my focus is on the emerging technologies. So we thought of using the FinFET and the tunnel FET types of devices. We use one of the lightweight cryptographic algorithms called present as the benchmark circuit, and all of our research is based on that. And then I will talk about some of the energy harvesting and sensor based development of the hardware security primitive, because all these IoT devices has the energy harvesting, because some of them are solar cell based energy driven, some of them are piezoelectric based energy driven, and there are a lot of sensors, like for examples. So these sensors are already available there. The energy harvesting sources are already there. Can we use these sensors and these energy harvesting sources for some additional feature of security? That's what I will show you today with some examples. So this is the primary focus, the energy recovery logic. That's what one of my major focus area is that. So you think in this way, whenever you have a normal system, if you take your classical CMOS book, you have the constant VDD source and the ground there, right? But in adiabatic circuits, you replace this by a clock. So you can say, instead of having the constant VDD source, you replace it by a clock. And this is dual rail logic. So you have the F and the F bar, the complement of that one. So now I give an example of this to give you an understanding of this idea through this seesaw type of thing, right? So you can consider that this clock is going up. So accordingly, you can say this is the clock going up. So the energy is getting transferred to your output node. So you can consider this your output node. This is your output node. The energy got transferred. Now, whenever I flip from 1 to 0, I send that energy to the ground. So there is always some dissipation happening. So what we are doing, we don't dissipate it to the ground, we recycle it. How do we do that? Because instead of having the constant VDD source, we have a clock here. So after some time, the clock will go up and the clock will start falling down also, right? So the clock is falling down, the potential difference will change. And because of that, you can think in this way that your source here has this lower potential, so energy is being recycled back. So I am not dissipating the energy now, I am recycling it, right? So this is the idea. In that way, you can develop some systems which are low power and also secure. I will show you some examples. So what we are talking about, usually when we talk about adding some sort of security, there is always some penalty. There is always some penalty. The penalty is in terms of increase in area, the penalty is in terms of increase in power consumption, But what I am talking about, can we develop a system which is secure while lowering the energy consumption compared to your conventional benchmark circuit. So, we lower the energy while making it more secure. So, please keep this in mind, that is what I am talking about. So, this is one example of the current consumption of a CMOS XOR gate. So, as you can see, if you transit from 0 to 0 1 to 1 0 and 1 1, your power profile is non-uniform, right. So, if you even from your eyes you can see that the graph does not look very uniform. So, it is much easy to attack these types of systems because the power consumption is much more non-uniform. So, you can easily do some statistical analysis and find out what is happening in the system. So, this one example to answer your question is the classical CMOS NOT gate, and this is my transition that is happening across 0 1 1 1, and accordingly this is the current that is flowing in the system. This is the, you can say, small peak, then no flow, then peak, then no flow, right. So, you can say still there is a non-uniformity here. Now, you can use also CMOS based methods. The idea the people use it, they call it dual rail logic, and so the idea is that by using dual rail logic you can balance your power profile. But if you use CMOS for doing that, instead of decreasing, the power consumption increases while making it uniform, okay. So, in this case you can see in this case it is 69 microampere, you can attack it, you use CMOS, make it dual rail, now it is uniform, this is high, no flow, high. So, you can say, but the power consumption has become, accordingly the power consumption is dependent on your current, right, because, so based on that it has become 142 microampere. So, in other words, I am secure now against some level of security against attacks, but what I am paying? I am paying more power consumption now, right. So, now the question comes is that how can I do both? I provide the security features and I also make my system secure. So, we use this adiabatic computing, and this is the last graph that I am going to talk about. You see, based on the input transition, my power profile is almost uniform, and this is 142 microampere and this is only 1.8 microampere. So, what we did? We suppress the peak current, we make it uniform, and the circuit is secure against attacks also. So, this is the method that we are proposing, okay, by using this adiabatic. This is the summary of the, if you look into more details, this is the paper that came in June 2001 on IEEE transition on emerging topics in computing. This is the whole paper, you can find out more details on that, okay. So, so we proposed one example, I will just go over the overall idea. So, this is the idea we propose of one of this logic. The idea is that this is the buffer. So, this is the logic you will have. This is the cross coupled transistors that will help to recover the energy. This is all the general idea. I will not go into the details, this is all in the paper actually, okay. But if you have questions, I will be happy to answer that questions. So, the idea is that you can create this type of XOR gate, the structure remains same. This is the part you will put your logic, one of them is XOR, it is a dual rail. So, you will generate XOR along with XNOR. This is the power profile, you can say the power profile is much more uniform, okay. This is general structure as I told you, you will have F and F bar here, this is the circuit that is helping you to, this circuit will be always there, this circuit will help you to make it adiabatic, and this is your logic here that is being embedded, okay. So, now this one example shows the power consumption of this, one of this adiabatic logic, and this is the one we proposed. I think I will show you with example with the CMOS base, okay, this is. So, now what we did, now you all of you got an idea of the adiabatic logic at the higher level. Now, let us look into deep where it is being applied. So, now this is an example of an AES cryptographic algorithm, and if you look into this way, this is the S box. And there are many algorithms which are block ciphers such as present and all those things. Many of these core component of these algorithms are S box, okay. And why we care for this S box, okay. We care for this S box because if you look into this power consumption, this is the breakdown of the power consumption around 10 megahertz. 75% of the energy consumption or the power consumption happen in this S box circuitry, right. So, that is a very good example for you to make this circuit secure if you try to take this as a small benchmark circuit. So, what we did, we tried to implement some of these circuits of this S box of with the adiabatic logic that I showed to you, and compared to CMOS, the power saving is by a factor of 14, right. So, this is 11.45 picojoule if you use conventional CMOS. This is another adiabatic logic that has 2.52. Then we propose this our method, you can say it is 0.825 picojoule and this is 13.878. Okay. So, the power consumption is a very good number, but I did not told you one more thing actually, which I did not talk also in the slide. Here we are also generating the clocks, right, instead of having the constant VDD. So, that clock should also be some sort of a resonator based clocks. So, that resonator based clock will also consume some power. So, it might be possible that based on the logic I am showing you an energy saving of factor of 14, but the clock generator will also consume some power. But based on our experience, you will still save at least 50 to 60% of the energy compared to conventional CMOS, even you consider the power dissipation of the clock generator also into a picture. So, the power saving number is still very good, and this I am telling you based on our experience because we designed the whole circuit including the clock generator. So, this is the energy comparison of the S-box circuit, and so now the interesting thing is that why IoT, why this technology cannot be used in all places, say example high-end high-speed processor, because you think it this way, this is a plot of the graph of this energy dissipation here, this is the frequency, you see here as soon as you increase the frequency after some time this adiabatic logic will be increasing the power to same as CMOS. So, this is the area around this one, it is more beneficial or you can say more power saving compared to CMOS. The reason is that the power dissipation in adiabatic is dependent on the time frequency T, it is RC divided by T, where T is the time period of your clock. When I say clock, I am talking about the power clock. So, if I run my system very fast, this means I have the smaller T, and so what will happen? My power consumption is going to get increased. Okay. So, this is the range, it is good, and that is why we talk about IoT applications, because this is the place where it is really giving you some energy saving compared to standard CMOS. Okay. But I am not denying the other methods, we are also looking into the methods from which you can try to see if this circuit work for further down, okay, further say example around this 1 gigahertz and all those things. So, there are also work related to that, you can look into the papers on that. So, now you got a general idea, now let us talk about emerging technologies. Okay. So, in the recent years people are looking into the emerging technologies, FinFET, tunnel FET, magnetic tunnel junctions. My research group have looked into all these technologies and tried to see, for example, there is silicon on insulator SOI technologies also. So, we looked into these technologies and we tried to see what the role these technologies will play in making your circuit secure and also lowering the power consumption. Okay. So, I will show with an example of FinFET. So, I hope that all of you are familiar with FinFET, but just to give you an idea, so this is your conventional transistor, this is a 2D device, but in the FinFET you raise this fin up, right. So, instead of having this horizontal here, this has risen up, it is more like a fin and it is rounded by this gate from all around, right. Here the gate is only here, but the gate is wrapped from that one. So, since the gate is wrapped from all around, you can say that it has low leakage because now you can better control your channel well from all sides. Okay. So, that is why you use this FinFET as device for controlling the leakage. So, now the interesting thing is that of course, it is saving us some leakage, does it provide us some more security? So, what we did, we look into the methods, we use save dynamic power by using adiabatic, leakage power by using FinFET devices, and then we use counter. So, now this one example of this FinFET base, this is the energy being dissipated here. So, what we did, this is the adiabatic, this is the conventional FinFET. So, if you the idea shows that if you use merge adiabatic with FinFET, the power consumption is much lower compared to using the normal FinFET. Now, the difference against FinFET and the CMOS is the number of fins. In your conventional 2D transistor, you can increase the width of the transistor based on that, but in the FinFET, you can increase the width of your channel by increasing the number of fins, right. So, we did a study and tried to understand that if I increase the number of fins, how does it play in the security. So, this is the idea, you increase the number of fins and how the security is going to play a role. Okay. So, changing in number of fin has no significant effect on security of fin cell gates, but this may be actually I was discussing with Professor Katkuri some time back, it may play a role if you do more analysis on faults and all those things, right. So now if you think in this way, another interesting is this can be suppress the current. So another thing we observe that this is the one of the things, waveform. One thing that I did not discuss with you is there is also a discharge signal. This discharge signal plays a role to make it secure. So the question comes, does the waveform of the discharge signal plays the role in the security? The answer is yes, okay, because what we looked into that, we changed the waveforms, and based on the waveforms we thought that if you change the waveform from this trapezoidal to the square, this is the square one, this is a trapezoidal. You can say that if it's trapezoidal, the current suppresses and the circuit becomes more secure. So you can also play with that waveform of that one, and accordingly you will see the security things changing. So just to give an idea, then power numbers, we already showed you big numbers. I am not going to detail because I want to give you some more insights on what research we do. These are power numbers. Then we provide some attacks on this one, and this is the CMOS based circuit. It is much easy to attack. The key is already out here. If it is adiabatic based bed, your system is correlating, but it is guessing the wrong key. The actual key is hidden here. So the interesting thing, by using adiabatic methods, you can make your system more secure, okay, because you cannot guess the key. So another thing you can think in this way. Here the correlation coefficient is 0.8. Here the correlation coefficient is 1 to 10 to the minus 3. So it's very, very low correlation coefficient. So the circuit is more secure, okay. So what we understood, by using the adiabatic logic, you can save power and you can make circuit resilience against side channel attacks, okay. Now let's look into more details. So now we got this idea. There is another transistor called tunnel FET, okay. This is another types of new transistor. The interesting thing I want to show you from this one is this graph. This graph is valuable because it shows that, so all of you know that you can save power by changing your voltage VDD, right. So this graph shows that if you plot the security, this is an NED metric that is called normal energy deviation. So if you plot the graph, then based on the voltage that you want to operate, which type of transistor can provide more security. So the idea shows that if you operate from 0 to 0.4, tunnel FET will give you the most security. After that, the FinFET and the CMOS. So you can think in this way. The idea it shows that this FinFET and this tunnel FET gates are more secure, but of course you cannot use tunnel FET in these technologies because tunnel FET don't work at this high voltage range. So if you go for below voltage range, then you go for tunnel FET and you will provide more security there, okay. This is some numbers, and these are again the numbers doesn't matter in that way actually, okay. So now let's talk about some other perspective, energy harvesting uses in the security. Now if you think in this way, if an IoT device is there, it has a power source can be the power from the nature, power can be battery, whatever. This is a transceiver microcontroller, you have sensors, sensor 1. This is the normal way an IoT devices work. So all of you have known this one, but my research group is focusing on using these sensors and energy harvesting sources for developing security primitives. So we develop this. What can be possible choices here? The possible choices can be solar cell, piezo sensors, thermoelectric, or whatever the energy harvesting sources. Here it can be sensor, it can be a piezo sensor, it can be a gas sensor, or it can be any type of sensor here, right. Can I use this sensor for security primitives? That's what we are looking into. So now what we do, this is an idea, this is an IoT device, this is a solar cell. So the solar cell is providing the energy efficiency. From this solar cell, we are developing a security primitive called physically unclonable function called puff. Now what is puff? I will tell you after this one. And the idea is that along with energy harvesting, you can also provide security through solar cells. So let's look into this example. So what is this puff? The puff is the silicon fingerprint. Like all of us have the unique DNA, right? The DNA of two persons cannot be same. So when you fabricate a chip or fabricate any sensors, two sensors, those two sensors will surely behave differently. Even suppose, let's think in this way, suppose I take two solar cells and I measure the current on the voltage produced by two solar cells, it will surely differ by a small, at least small fraction. And if you put a right algorithms, then you should be able to capture that variation. And that's what we did. We developed some algorithms that can capture those variations. This is an example. So if you think in this way, it is an array of 8 solar cells. This is the microcontroller. We use the Texas 2-bit microcontroller. It feeds that. This is the whole system, and we develop the idea from that. The idea is that you can think in this way, 1 puff and 2 puff cannot behave the same way. So this is the idea. There is a couple of array of solar cells. It feeds into that, and from that we are creating a unique identity for an IoT device. This means I can identify one IoT device from the other IoT device, right? So it's providing the security feature. So the idea, what is more important, this is what is more important. Building proof from existing sensor energy harvesting devices has the potential to mitigate cyber threats in edge computing with minimal redesign cost and performance penalty. This is the key, minimal redesign cost and performance penalty, because we are using the existing component that is already available in the IoT device. So now next move further. This is application of puff. This is another example, and in this one you can think in this way. These are different types of sensors. Previous the idea was the energy harvesting source. So we use solar cells, we have piezos. I can explain you more on that if you want, but I want to give you the high level picture. So this is the sensors, different types of sensors. Can we use the sensors for security? So the answer is yes. We have used these piezo sensors, and we developed this physically unclonable function based on piezos. This is another example. We have used these thermistor sensors, the temperature sensors, and from the temperature sensors we have created these security features. And now in the longer pictures, you can have these cryptographic processors, sensors. This is puff, 2 random number generation, and all this being generated from sensor energy harvesting source. So your system will be overall looking like this in the bigger picture when you talk about IoT and security. Okay? So all the security primitives such as TRNGs. My research group is also looking into this 2 random number generation from sensors. We have a paper coming out in that direction also. So all these things, like how can you develop 2 random number generator, puff, and all those things from sensors. Now the last thing that I want to talk about is the vehicle cybersecurity, because my research group is also looking into that one. So now if you think in this way, this is the one of the special issue we edited with Professor Mohanty and Dr. Stacy Provol from Oak Ridge National. We edited a recent special issue on vehicle cybersecurity. So the issue is that, you know, the new vehicles that you have are no longer, you can think, of mechanical systems. They are each, can you imagine how many lines of code your car has? The car has around 100 million lines of code. That's a big number, 100 million lines of code, software code inside your car. Around 60 electronic control unit. This electronic control unit you can consider more like a microcontrollers or microprocessors. There are a lot of electronics inside the car now, okay? And many of these cars communicate right now through a bus. That is called the CAN bus. It is called Control Area Network Bus. And this bus is not encrypted. It is completely unsecure, so anybody can attack it, okay? There is an OBD port in your bus, and that is called onboard diagnostic port. So you can throw that, you can sensor, capture the signals, and you can perform some side channel attacks, insert malware, or whatever you want to do, okay? So this special issue has all that. This special issue come in November, you can look into more details, but that's the idea. So what is that? So this is the cyber security of the vehicles. So this is your car. The car has, this is vehicle to vehicle communication, this is dashboard, powertrain, everything is electronics now, everything is most on IoT and sensor based. This means I need to make them secure. When two cars, now let's think in this way, I am going on a highway, and it's vehicle to vehicle communication, and the weather is very bad, okay? Now the weather is very bad, and if there is a malicious car going in the front, you know what? There is a chances that your car can fall or can cause accident, but the malicious car is sending you the incident, the message that everything is fine. So how will you know that what is the real intent of the front of the car? So there is a lot of cyber security issues involved in that, right? Or say example, the driving limit is only 45, but the front car is showing that it is fine to drive at 70. So how will you make those decisions? So vehicle to vehicle communication, authentication, all those things are a big issue in the future. So when you talk about autonomous car, how will you make sure that when a group of cars are moving around, some malicious car enter into your fleet, how will you identify it, right? So there are a lot of issues in that. So similarly, suppose let's think in this way, a lot of electrical vehicles are coming into the picture. So suppose you want to charge your electrical vehicle, you plug your smart plug to that grid. What if is not some Trojan into your grid? The whole grid collapses now, right? So you need to also make sure that there is secure authentication happening before the information is or the energy is being transferred between the car and the smart grid and all those things, right. So it's a really big challenge, okay. So now if you think in this way, in these systems, this is an example of the hardware security module that happens inside the car. It has couple of crypto engines. This is the symmetric crypto engine called AES. This is asymmetric AES, hash engine, DR engine, all those things. So you can think it's a hardware security module. Now, as I told you, there can be different types of malware and security attacks, but there is also quantum computing coming, right? And when the quantum computing is coming, the idea is that the quantum computing can break all the encryption engines. Most of them, like for example, this asymmetric crypto engines such as IEEE-iSES and RSAs will be broken down once the quantum computing comes into picture, right? Similarly, symmetric crypto engines are resilient against quantum attacks, but of course the key size has to be increased. So now in other words, you also have to think, because why we have to think? Because once you buy a car, you can change your phone after 1 year, but you buy a car, the car is going to stay with you for at least 20-30 years. And what if within the 20-30 years the quantum computers come into picture? So you can change your phone, you can change your laptop, but based on my experience, you buy a car, it stays with you at least for 20-30 years. So what if by the time quantum computer come into pictures and people start hacking your car? So you have to also think in that direction, that can I make my car secure against quantum attacks? So post-quantum cryptography is another area, okay. This is one of the things that I want to emphasize to you. I won't go into all these details. These are all the type of attacks and all those things. These are taxonomy of the different types of attacks that is possible in the car. Last application that I want to talk about, I talked about PUF and how the PUF can be used. One application, there are several applications of the PUF. This one example shows that, let's say you buy a car from Toyota or a Honda or any car, right? Now they want to remotely update the software in your car, right? So usually they do that, and there is an encryption engine beside that. But the issue is that suppose somebody has a malicious intention, it performs some side channel attacks and all those things and get the keys, and then somebody can put some, I don't know how many of you read it, but there was a news that people have uploaded the ASUS laptop with some, not with the real update, but with the malware update. This same thing can happen in your car, okay? Because suppose, how will you know that the authentication or the real software is being uploaded by Toyota? It can be some malware sitting somewhere, okay? So the idea is that you can create a secure gateway along with a PUF, the physical unclonable function, and that can help you in the secure communication, okay? So now I talked about, this is the solar cell I talked about. I told you that you can develop security primitives from solar cell. This is an example of a car with a solar panel on the top. And there is, solar panel means there are thousands of solar cells, small, all of these, right? So I can easily develop some security primitives from this one, right? Okay. So, and this ECU scans and all the thing can be secure. So vehicle security is another important research area. I don't know how many people in India are working on this one, but definitely I will encourage you all to look into that, because it has a lot of potential. And today or tomorrow, I know that it's very difficult to drive an autonomous car in India, but who knows what will happen in the future, right? So it's a very, very nice area for so many of you who are looking for the many of you young researchers sitting here, you can choose vehicle security as a thesis topic. It's very interesting, okay? So these are some of my sponsors, and I like to thank my graduate students who have worked with me and have produced really, really good quality results. So with that, I like to end my talk, and I'm happy to answer any question that you have. When you say technology, you mean to say that like 130 nanometer, 45 nanometer? Yes. See, to my understanding, the manufacturing variation will occur in any technologies, okay? So we recently simulated a PUF in 180 nanometer, and then we simulated a PUF in 45 nanometers. So to answer your question, I think what you want to ask me is that how the reliability numbers will change based on the technology. So that's a very important thing. So I think when we create these types of circuits, we need to do some simulations and take few technologies, because it might be possible that, say example, the reliability number is 98% in 180 nanometer, but when you go for 45 nanometer, it is only 94%. So you have to take few technologies, and based on that you need to perform analysis where it is providing some more. So you can, in other words, everything in a PUF you can measure in some of metrics such as uniqueness, reliability, uniformity, and all those things, right? So you perform some simulation based on technologies before you actually go for chip fabrications, get those numbers, and then that is the technology that you want to look for.
Yes, sir. So, sir, if we go for a lower technology to achieve the security, because for a various probably we should achieve for a lower technology, okay?
Right.
Then how would we cost effective? Because we are talking about the thousands of the solar cell, and at the same time we want to achieve the security at
Yes.
the cost of the cost. So
yeah, so this is exactly, so this is what I'm talking about based on my experience with talking with industry experts. So when I talk with industry experts, like I won't name any companies, but just to give an example to you, they won't care if you fabricate an IoT chips at 20 nanometer, 12 nanometers because it's too expensive for them. So when you talk about IoT technologies, they will advise that fabricate in 45 nanometers, even 130 nanometer is good enough. Because here you are talking, see, depend on the application. If you talk about IoT, you want to have an IoT device in cents, not in dollars, right? So in cents, this means I need to go for even older technology node, that's fine, as long as the cost is fine and it's doing the job that it's supposed to do. So go for higher technology node if you're talking for IoT. For example, in my research, I think I will be fine with 130 nanometer, and the reason I will tell you why, because if you go for lower technology nodes, the leakage is also going to be very high. 130 nanometer is one technology node where you will have some sort of right compromise between a leakage and other important benefits, and the cost also. So based on our experience, actually, we took several technologies, but we dropped some of them because we think it will be difficult to fabricate and on a large scale. But in my opinion, because magnetic memories are already in the market, static STT-MRAM based memories. So that's why we are looking into logic in memory circuits right now, because we personally think that that could have good fabrication chances, because the MRAMs are already becoming big in the market. There are already 2 GBs, 3 GBs MRAMs or more than that available now. And if you integrate CMOS, the integration of CMOS MTJ type of circuits could be much easy. Or similarly memory stir type of thing, right? Whichever. So in other words, I think it is good idea to put bet on those technologies which people can fabricate the bigger circuit. Even if you get very fancy results and the fabrication technology is not possible, then it's not a very good idea. So thank you everyone.